Hello everyone. Welcome to the NPTEL course on Introduction to Astrophysical Fluids. My name is Rohan. I'm a TA for this course. I'm a PhD scholar at IISc Bangalore. So before we start today's lecture, we'll just start with a brief recap of previous week, and then we will start with today's content. So today mainly we'll be talking about the MHD equations and their consequences. Uh, and we have already introduced plasmas in the previous week. So, so this is just a brief recap of the previous week. So, so we started with the effect of rotation on a self-gravitating mass, right? So, so whenever a star is rotating or another object is rotating, it takes the shape of a spheroid or an ellipsoid, like we have seen in the previous week, that it could be, I mean, mostly it takes the shape of an oblate spheroid. And the equation of the spheroid is given like this, as is shown here, which is the equation of the, a spheroid basically. So, so this is the omega is the angular velocity of the object of the self-gravitating mass. And if you see, this is the equation of a spheroid. And if I write it uh, like this in terms of the eccentricity of the spheroid, you can write the equation like this, right? So where alpha naught, beta naught, and gamma naught were could be expressed in terms of A, B, and C, which were uh, the semi-major axis and the minor axis of the uh, spheroid. So, so you can write the angular velocity in terms of the eccentricity of the spheroid in this form. And so this is the plot of the uh, angular velocity square over pi g rho with eccentricity. So if you see, like if as eccentricity increases, there comes a point where the omega reaches the maximum value, right, which is somewhere between zero point 0.4 and zero point 0.5, and this is the eccentricity at which you know uh, the omega is maximum. And why this happens, in order to look for that, we also studied how the angular momentum varies with eccentricity, and we saw that the angular momentum uh, do- doesn't show any such maximum. It in fact increases, and you know as we go to higher and higher eccentricities, the angular momentum it increases even faster, right? So, so that was what the effect of rotation could do to some self-gravitating object, right? Now, we have seen that this effect of rotation has been it is very minimal or very negligible in the usual stars, for example, our sun, right? And other sun-like stars as well. But the effect of rotation becomes important in case of a collapsing star, which collapses, and that we also see, we also saw in the last lecture that how uh, and why it is actually important for the collapsing star. So if you look at this equation, so this is the equation of the basically the momentum conservation equation, including the centrifugal effect and the Coriolis effect as well, right? So we studied these two extra terms and how they come if we consider rotation, right? So, so we can express the momentum conservation equation in this form, and therefore, if you see, the phi becomes phi effective, which is basically phi minus the half omega cross r whole square, which is the centrifugal term. So instead of just the gravitational potential, we have an effective potential, which is the gravitational potential along with the centrifugal term. Right. So, okay, now why is the you know the centrifugal effect or the rotation effect of rotation is not important in uh, normal stars is because you see that this omega cross r, the centrifugal term, is very less compared to phi, right? But in case of a collapsing star, this is not the case. And why is it not the case is because you see the moment of inertia is proportional to a square. A is the radius of the star. And as the star collapses, its radius decreases, and therefore the moment of inertia decreases. But in order to conserve the angular momentum, which is I omega, the uh, the angular momentum should increase. Right? And so the centrifugal acceleration, which is omega square a, should also increase. And the gravitational acceleration, which will also increase, but it will increase as a to the power of minus 2. But centrifugal acceleration increases as a to the minus 3, and therefore has you know, a faster rate of increase compared to the gravitational acceleration. Right? So, so you see, that's why. I mean, as a star collapses, the centrifugal acceleration, overtakes gravitational acceleration at some point, and this, in the phi effective, the second term becomes important. And we also did an order of magnitude calculation and showing that, well, from this graph, is that so omega square should be less than 0.44950. The 449 is the maximum value of this graph. And if we do, so this will reduce down to, so T is just 2 pi by omega from derivative of T in terms of rho. And we also showed that the rho is typically 10 to the 8 gram per cc for a white dwarf and 10 to the 14 gram per cc for a neutron star. And accordingly, we calculate the time period of rotation of these objects, white dwarfs and neutron stars. And these come out to be something like this, right? Which is pretty close to uh, close to what we observe. So that was the end of rotation and fluids. Basically, now we moved on to a new topic, which was plasma. We'll continue it in this week as well in the coming weeks. So So we studied that, like uh, as you heat up uh, solid, it turns into liquid and then to gas. And further, if you heat up the gas, furthermore, what will happen is that the gas will ionize. So the electrons will separate from the nucleus, right? Like has been shown in the figure. And they will form free electrons and free ions, right? Which will move on their own. So these can be thought of as, background of ions and electrons moving freely within the background of ions or the potential created by the ions. So yeah, so that is what the basic description of the plasma is. So we actually studied about two more important concepts related to the plasma. So one is the shielding effect of the plasma, which is the Debye shielding characterized by the Debye length. So it states that so as you have free ions and electrons in the plasma, the ions will try to attract the electrons and it forms a you know kind of a shell around it, it shields the rest of the electrons from from coming near to it, right? So so that is the distance, the characteristic distance that defines that length or of the shielding, that is called the Debye length, right? So we did I mean, pretty exhaustive calculation in the previous week where we said that del square phi is the electric potential is, this is just the Gauss law, right? The del square phi is rho by epsilon naught, rho is given by n naught minus n e, n naught is the ion density, ion number density, n is the electron number density, and uh, by solving this equation, we found the solution to be phi equals to like this. If we plot this, so this is how it looks like phi as a function of r, and this lambda d is where this uh, this drop of the electric potential happens. So after a certain distance, that is when lambda d, the phi electric potential drops. So after this, the ion at the center won't have much effect to the outside uh, particles, right? So that's why it's called the Debye shielding effect. Another important concept we studied was that of plasma oscillations, so which we did by by displacing a slab of charge slightly by delta x amount, and then we have ions and electrons separated, and this will create oscillations of this slab, which we which can be expressed as a simple equation of d2 del x del v square equals to some the equals to the force, right? So force is q times e, right? And from there, the frequency of oscillation could be uh, estimated in this form. Right? So these are the criteria of the plasma, which is that the omega p tau c should be greater than 1, L, the length of the system should be much greater than the Debye length, and the number density or the number of particles inside the Debye volume should be much greater than 1. And we actually physically motivated each of these conditions in the previous week. Right? So we will continue our discussion in today's week from here, and we will see. Um, we'll dig more deep into these concepts, and we'll study about plasmas more, and we'll finally derive the magnetohydrodynamic equations from here. So, any questions till now going up to this? Okay, so if not, let's move on to this week's material. Okay, so we will first take a statistical approach to uh, deriving the magnetohydrodynamic equations, just like we did for while doing the hydrodynamic equations of fluids, like the Euler equation, Navier-Stokes equation, and so we will take a similar approach, but we will not go into much detail this time as we did in the previous case. But the approach will be similar. So we have already studied about the density distribution, and which is represented by Fs, right? And the number density is defined like this: Fs times over P3V. So we have studied about the phase space and all, right? So Fs is the density distribution function uh, uh, over the phase space, which is defined as R and V, and integrated over D3V would give you the number density. And similarly, the average velocity is given as 1 by ns dfs d3v. Kinetic energy half ms v square fs d3v, and the pressure tensor as ms v minus us times v minus us fs. So these are the definitions, right? And so these definitions are actually same as what we did um, earlier while deriving the uh, hydrodynamic equations, right? So, so So we will consider a small volume in the phase space defined as d3x d3v, and as the phase space evolves in time, we will track this volume, and the at some other next instant of time at t plus dt, this volume will become d3x prime d3d prime, right? So this is the picture in absence of any collision or scattering. Whereas, if we have some scattering or collision, there could be particles coming out or particles coming in to the volume at the next instant, and the picture will change, and we'll have a collision term like this del CF del T. So, so this is the Boltzmann equation which we will study, and this is the Vlasov equation, right? In case of our MHD approximation. So we will just quickly derive how Boltzmann equation comes from this picture, and from there, how can we go to the Vlasov equation? So let me quickly go to the whiteboard. Okay, so we have studied that the phase space volume, volume of the phase space should remain constant. That's the Liouville's theorem, right? So we have derived those in the first or the second week. So so uh, so we are not going to do it again, but we are just going to use the theorem in deriving the Boltzmann and the Vlasov equation. So this is just coming from the conservation of the phase space volume. So this is at time t, this is at time t plus dt. So how does xr change? The xr, so I am writing the subscript r because we are considering different species over here. So r represents for a single species. So this is how the xr and the vr prime, basically the x and the v coordinates changes with time. And so you see that we can always write the uh, uh, the x prime and the v prime coordinates in terms of the x and v coordinates with some Jacobian. So this is just a transformation of coordinates, right? So for example, when you rotate a coordinate, you have the rotation matrix attached to it. And similarly, so this is just a Jacobian which has the form like this. So this is determinant of dx prime dx dy prime dx dot dot dot, and then dx prime dy prime dy, and this will be a 6 by 6 matrix dz prime dz. So all this will be partial derivatives actually. So this is the Jacobian. And this is a 6 by 6 matrix. So this is how a Jacobian is defined. So now, if you just use these two identities, so del XR, del XS, well, sorry, so XR and BR do not represent different species, so they just represent different coordinates. So R is basically X, Y, and Z, this, right? So they are not different species. So we'll come to that later on. Okay. So R is X, Y, Z, and similarly S here is also X, Y, Z. So del XR prime del XS is delta RS, and del X R prime del Vs is equals to delta Rs dt. So this makes sense because del Vs is basically del Xs by dt, right? And this will be just like this. So, so if you use these two identities, okay. So if you use these two identities, the Jacobian will simplify a lot, and you will finally find that del 3x prime del 3p prime is simply reduced to this form 2 plus delta v bar and fr by m dt d3x 3p. Okay, so this is uh, what will become. Now, we're just gonna put this into the main first equation, the conservation of the phase space, right? And if we do that, let me so if we do that, we'll see that f prime is equals to f plus del f del t dt, the summation of the r v r del f del x r dt, the summation of the r f r by n del f del r dt, right? So, okay. Okay, so actually, right now we are not putting it into the equation. So, yeah, the same. Okay, so this is just coming from the uh, Taylor expansion of f prime around f. Okay, so not yet. So we haven't yet put the T3. We haven't used the expression, this expression yet. Now we will actually put the expression. this value over here. So we'll replace f prime with this, and we'll replace d3 x prime d3 p prime with this, right? And yeah, so so f d3x d3v is equals to f prime d3x prime d3v, and so f prime is uh, gotten from the above equation, and then d3x prime d3v has some part and d3x d3v. So this d3x d3v will cancel with this, and then if we equate, it will be f equals to f plus del f del t dt, the summation over r vr del f del xr dt, the summation over r fr by m del f del vr dt, plus summation over r f del vr del xr dt, the summation over r f del xr fr by m dt. Okay. So yes, so there will be a few cancellations over here, like f will cancel with f, and so we can do a few more things. So for example, we can take this PR inside the derivative, because the derivative of PR with respect to XR is already zero. This term will cancel for that, and and we can combine these two terms into a total derivative of f and fr by m. Okay. So finally, we can write as del f del t plus, if I take this inside, so this is the summation over r, then del xr of PR times f. And if we combine these two terms, this will be a total derivative del VR of fr by m times f. Okay. So yeah, so this is just using chain rule. If you break it up, so this will be f times derivative of this thing, and fr by m times derivative of f. Okay. So this is the Boltzmann equation that we get. Okay. So any questions still no, or makes sense? Okay. Okay, so that was the Boltzmann equation, and from there, uh, if we have to just derive the Vlasov equation, uh, right, let's see. So del Vx of fx by m, okay, is equals to So here, when we talk about force in MHD, we'll be talking about Lorentz force, which is Q times E plus V plus V, right? So we all know about this. So the x component of this term, uh, what this will be- so this will be x plus By Bz minus Bz By. So it is V plus P, right? Right. So you see that Ex is not dependent on the velocity. And similarly, By, Bz, nothing depends on velocity. So therefore, we see that the fx by f term is independent of velocity. So this term, so we have ddvx of fr by m. So this term is independent of velocity, so we can take this out. Okay. So our final equation will be del f del t plus summation of r vr del f del xr. So also in the second term, if you see vr and xr are independent variables, right? So we can also take so del vr del x s is equals to 0. So we can take vr out of the integration as well. And then del vr, but fr by m out of the derivative. Oh yeah, like this. So we can write the equation like this. And finally, if we write it in vector form, this will do by m del v dot f and just 0, right? Now this is the actual Boltzmann equation in absence of any collisions. But if you remember that if we have some collisions, and we will later on see how we can formally write collisions in in uh, in a MHD framework. But right now, in presence of collisions, we'll have this extra collision term. Right? So that is it. Right? So this is the Boltzmann equation, which we saw in the slide. So this is it. And if we just replace the force over here with Q times E plus V plus V, which is the Lorentz force that we saw, so we'll just uh, get this lasso equation. Okay. Now we will talk about uh, you know obtaining the chemist equations from uh, this lasso equation. So if you take the zeroth moment, you get this uh, equation, which is the continuity equation in this case. So remember, you can see that we have a new term, which is the del dot J, which is the current. Okay. So del rho del T plus del dot J equals to 0. And similarly, this is the first moment. Uh, so if you remember, by taking moments, which we also did back in while we are doing the hydrodynamic equations. So while we are taking moments, we mean that integrating this equation over the whole phase space, like doing d3x, d3v. And by zeroth moment, we just mean that basically velocity to the power of 0 should be multiplied with f. By the first moment, we mean phi to the power of 1, or phi should be multiplied with fp and then integrated over. Similarly, for second moment, phi square will be multiplied with f and then integrate over. So we will just see how it happens. we'll just derive the moment equations. But before that, let me just tell you that this is the equivalent of the continuity equation. So this is uh, the momentum conservation equation. So ms ns dus dt. So this is the total derivative. The total derivative is del us del t plus u dot del uh, u. Right. So here S stands for each species, and by each species I mean electrons, ions. So they are two separate species. So you can write this equation um, for electrons and ions separately. So Ns is the number density, Ms is the mass of the species, us the velocity, Es is the charge, E plus us times us cross V minus del dot Es, the pressure tensor, plus the collision vector. Right? And similarly, the second moment, so del Ws del T plus del dot Qs, Qs is the heat flux, E dot J, and this is coming from the collision term, right? So, yeah. So, okay, let's see how, well, Ws is the energy, total kinetic energy. So we will see how this equation comes about, and let's just go to the thing. So, okay, so let's start with the Boltzmann equation. Well, let's write the conditional term as well. Okay. So now, if we take the zeroth moment, the equation will be volume integral del fs del t del 3v. So you see that we are not, so since it's zeroth moment, so this del fs del t. So when it will be first moment, so it will be v times del fs del t. So there will be t multiplied with it. Similarly, for the second moment, p square will be multiplied with this term. Okay. So this thing plus 1 by ms f dot del 2 fs del 3 fs cfs del del 2 del 3 right. So if you remember the original definition, like we were discussing in the slide, so we'll use these definitions of ns, us, ws, ps. So, right. So if you see the first term, so the first term is del fs del t d3v. This could be written as del t of integration of fs d3v. And the inside part, this part is just ns by definition. So this will be del ns del t. Simple. So that's the first term. What about the second term? Second term is v dot del fs d3v. And we can actually take the v inside the del, inside the gradient. Right? Because if we expand this, it will be fs del dot v plus v del fs, right? V dot del fs. But fs del dot v is equals to zero because we saw that velocity and position are independent of each other, right? So del v del x is zero. So this will be same as this. Okay, there is d3v and then this will be ns us, where us is the average velocity. Okay, so by definition. Okay, using that definition, we get this. What about the third term? So let me see. So this is the first, second, third term. So so the third term is del phi. So okay, let me first write down f dot del phi fs d3v equation. So this is the third term, right? Now let's see if we can simplify the third term. Okay, let me try to do what. Wait a minute. Okay, so for this, we will uh, use an identity, so which will derive like this. So V cross B is epsilon ijk bj bk. So this is the formula for cross product. And if we take del V dot B cross B, that is del of B cross B I del Vi, right? So that will be del of epsilon ijk bj bk del Vi, right? And that will be epsilon ijk dk del Vj del Vi, right? And well, because the magnetic field do not depend on the velocity, so this will be just like this, and this will be epsilon ijk dk, and del Vj Vi will just be delta Ij, right? And therefore, this will be epsilon Iik Vk, and due to the properties of this epsilon, so if there are repeated index of the Levi-Civita symbol, so this will go to zero. So this will become zero. So del V dot V cross B is zero, right? So why we're doing this, right? Why we are using this and why do we need this identity is because the force in this case is V cross B, right? The Lorentz force is V cross B. So since del phi of V cross B is zero, so therefore del V dot this thing is equals to dot del VFS, right? Because, well, del V of the whole thing, right? The whole thing is, so we can just take this out because the derivatives of this thing is zero. So, right. So this is the force. So F dot del VFS, right? So this is over here. So F dot del VFS is equals to del V of FFS. So that's why we need this. And this will be del V dot FFS in 3V. Now, so you see, now we will use the uh, divergence law, right? So this is del V of something integrated over volume is basically the surface integral of the quantity over the enclosed surface, right? And if we take the surface to be large enough, we see that the Fs, the distribution function, vanishes at infinity. So this will become zero. Okay. So we have the first term, second term, third term, right? And the last term, the fourth term, let me write it over here. Okay. So this is simply del CFS delta T d3V, and this will be equals to delta T of Fs d3V, which is equals to delta CNS delta T, which is again zero because the number density do not change. Right? The actually the number density do change, but the number of particles do not change. Right? So right. So therefore, this will become zero because of number conservation. Okay, so the third term and the fourth term are zero. What we are left with are the first term and the second term, right? And if you see, so this will just give us the desired equation, right? So del rho del t. So rho is just mass times the number density, right? Let me just write it down just for completeness. So rho is ms. So if you just multiply m with this, so you'll get del rho del t, right? And so this is just the current. The current is defined as ms. Yes. So this is the current. So the equation just becomes del rho del t plus del dot j, right? If you just multiply with ms, so this will become j and equals to 0. So that is how the equation, the zeroth moment equation gives us the continuity equation, right? So, yeah, is there any question? Makes sense. Okay. So, That is fine. So similarly, we can derive the first moment and the second moment. So the first moment will just simply be this equation. So we are just multiplying the equation with v. Right? So if you similarly, simplify this equation, you will get the equation for moment of observation, which is this equation. So I will not derive this equation over here, but because it's a bit lengthy, but I will post notes where you can see the derivation of this equation step by step done, right? But this should be straightforward. And simply for the second moment, so you can just replace this v with v square over here, v square, v square, v square, and then you will arrive at this equation. It's the equation of the second moment. So I will also post notes for how to derive the second moment as well. So it's a bit lengthy, but you can see the derivation. It will be same as the how we did the zeroth moment and using these definitions. Okay. Right. Okay. So okay, moving on to the next topic, which is the MHD equations. So how can we derive the MHD equations from the moment equations that we just saw? Right. So basically so we'll do the MHD equation step by step. So this is the mass contained equation and this is the momentum equation. So we will do these two first and then later go on to the energy equation. In between we do some other stuff. But let me just first derive the mass contained equation and the momentum equation just from the zeroth and the second zeroth and the first moment actually. The second moment will give you the energy equation. So let me go back again over here. And open new notebook. Okay, so as I said, the S, the subscript S, actually stands for species, right? So if we have different species, so the density, total density, will be given like this, summation of all the species. And similarly, the velocity, well, the mean velocity of the fluid, not the velocity of the individual species. The mean velocity of the fluid or the plasma will be given like this. So where rho ms is the uh, is the density of each species, us is the velocity of each species, u is the total fluid velocity. Right? And and just using these definitions, you can see that That's a continuity equation reduces down to this. Because what was there over here was J, which was MS, NS, US, right? And yeah, so MS, NS is just rho MS, right? So this is rho MS times US. So this is the continuity equation. So that was simple. The momentum equation takes a little bit of work, but we will go through it step by step. And let's see. So momentum equation. So, so what we'll do, we'll sum over all the species. So we are just coming from, starting with this equation, okay, the first one, and then trying to derive the momentum equation from here. So, for example, the first one is MSNS. So MSNS is rho MS, right? And times US. Okay. So yeah. So I'm just rho MS times US, and I can take the rho inside. So, and also I'm summing over all the species. So rho MS US US equals to. So this is total derivative, right? So I can write it down as partial derivative plus u dot del. So that's what I'm doing. So this is the u dot delta, and this is rho q e plus j cross p. So this one is the rho q. So rho m is msns. So rho q is esns, okay, or nses. So rho q e plus neus is j cross p. And then we have del dot PS, which is the pressure tensor. The summation of S, del S, PS, del T. Right? So this is true. Let's confirm. So, so the definition of PS is already given over here. We are just going to define another quantity, which is defined like this, which is P naught S, which is PS plus rho MS WS WS, where WS these are vectors. So WS is US minus U and is called the diffusion velocity. So right. So US, as I said, is the velocity of each species, and U is the velocity of the fluid, right? The main velocity. Right? And and P naught S over here. So this is the definition of P naught S. So what I'm writing now is the actual definition of P naught S. That was T3V. So if you remember, PS is V minus US, but for P naught S, it's V minus U. So it's the velocity minus the velocity of the fluid. Here it was the velocity of the species. Okay. So that is the relation between P naught s and Ps. So this is a simple, straightforward algebra. You can just see, you can just expand P naught s and Ps written over here and add this term, right? Where W is given like this, and you can see that the US will cancel, right? And you will get P naught s, which do not has any US. Okay. So the US will cancel with uh, this term. The US contained in PS will cancel with this. We just do that with this. Okay. So, right. Okay. So the definition which I said of rho Q is NSES, J is NSES and P naught. I'm just defining it as summation over P naught over all species. Okay. Right. So what else? Right. Now let's just write the equation as is. So what we can do is just we can just replace this with P naught, right? So I'm not writing it again. Just say this is P naught, right? And yes, okay. And so all this US you see over here. So now we can uh, actually replace US with WS plus U, right? WS plus U. So by doing this and using this equation, right? So this is our main equation. This is our main equation, and let's write down the left hand side of this equation. So what will become is del del T of rho ms u. We're just replacing US with WS plus U plus del del T of rho ms WS plus del dot rho ms WS WS plus del dot rho ms WSU plus del dot rho ms UWS plus del dot rho ms U. Okay, so a lot of terms. Okay, so okay, so we can use one fact that is rho ms times ws is equals to 0. So that this will basically come from the fact that ws is us minus u, right? So this will be rho ms us minus rho ms u, and rho ms us, if you do summation over all the s, right? So this will actually become uh, rho ms times u minus. So it will become actually mu minus mu, right, over all the species. So this will be zero. So if we use that fact, then actually a lot of terms will cancel. This one will cancel. Yeah, I guess that's right. So we're left with del del T of rho ms u plus del dot rho ms uu and del dot rho ms ws. Right, three terms. Well, this will also. Hmm, think this will also. Yeah, then I guess we are done because then then the LHS simply reduces down to del del T of rho and u plus, let me make some space first, or maybe you can just pretend. So del del T of rho and u plus del dot rho and u bar and del dot rho and u bar equals to rho QE plus J cross P minus del dot E naught. Right. So, so these two terms from the LHS and the RHS is this. And this is what the momentum equation is. This equation. Yeah. So, right. So this term is just the u dot del term. U dot del u. And so we will come to the energy equation. But before that, we want to uh, derive some of the other stuffs. And as we know that the energy equation is actually decoupled from the uh, momentum and the mass content equation in a lot of cases. So we can actually uh, do away with the energy equation in most of the cases. So before we go into the energy equation, we just want to uh, derive something which is called the generalized Ohm's law, right? Which was just touched upon on the in the lectures, but it wasn't derived completely. But we want to see this equation and derive it on the first principle, and uh, and this is how the equation looks like. So basically, uh, what I guess you are familiar with was you have studied J equals to sigma E, right? But that just tells you an incomplete story. The generalized Ohm's law is this whole thing, right? So what we generally see is this only the left hand side part, or even J equals to sigma E, not even the E equals B term. But the actual equation is this thing, and we'll just see how this equation comes about. So so for this we don't need anything. We just need the momentum equation, right? Or uh, basically what we'll be using is the first moment. So this equation we'll be using, right? Which we haven't derived, but I'll share the notes. Okay. So so yeah, right. Let's go through it. So if you just do a simplistic derivation of Ohm's law, I mean you can just write it like this, right? J equals to sigma E. But E, as you know, well, I'm writing prime because this depends on the coordinates. And if you just do a Lorentz transformation of this electric field, it will be something like this, right? Whereas J prime will just be J. And therefore, J will be equal to sigma E plus U plus P. So this is the general, well, not general, but the Ohm's law that we are familiar with. But the generalized Ohm's law contains more terms and is the more complete form. This is just a partial story. Right. Now, let's look at the collision term in the first moment equation. So we just want to write the collision term as something like this. So when we are studying collisions between two species, let's say S and R, so it will depend on the difference in velocities. This is the collision frequency, mu SR, ns is the number density and the mass, respectively. So this is how we physically write the collision term. And now what we'll do is we'll just write the first moment equation as is. We have derived del T as Ni ui bar is del dot Ni ui. So there's the vector one. So first to Ni, sorry, Ni E plus ui plus P. So I stands for ions. So we're just gonna write the equation for ions first and then for electrons. So this is the collision term Ni nu IE ui minus Cu. Similarly, we can write this equation for electrons. And so this is the so this is del u del t term, and this is u dot del term. And then on the other side, we have minus Ne because the charge for electrons are negative. Then we have the Lorentz force term, E cross E, the pressure term, minus N, the collision term. Right. Okay, so now what we'll do, this calculation was not done in lectures, so I thought maybe we can do it more explicitly. So we'll just multiply the first equation with Me and the second equation with Mi, and we will just, subtract the second equation from the first, right? So let's just see. So this will be Me and my del t of n ui minus ue plus del dot n ui minus ue, right? So this is this minus this term, and this will be del dot. So so n is basically Ne and Ni. So we just assume that since it's a so n equals to Ne minus Ne equals to Ni, since the plasma is um, neutral, charge neutrality holds. Okay, so right, so this is equals to E rho m E plus En Ne Vi minus Ni E plus P minus Ne doing what Pi. Mm, So Me del dot Pi, and then this will be Mi del dot Pi plus Mi del dot Pi minus Mi mu IE, the collision term, plus Mi N mu I, right. Okay. Okay, so this is a big equation, but we'll just look at it uh, one term at a time. So let's just let's look at um, which term. So the first term, so this is just G, right? Okay, another thing to mention is that rho m equals to n Me plus Mi. So this is the density, which is the total density of the electrons and the ions. And N equals to Ni equals to N, which you already mentioned. And also, Mi nu IE was equal to Me nu EI, because, well, the ions and the electrons are colliding. So whatever the force the ions are exerting on the electrons are exerting on the ions due to Newton's theorem. So, right. Now, let's look at the terms on. So, therefore, yeah, like I was saying, that the first term is basically J, right? So, this will be del J del T. Okay. So, J, if you remember, the definition was mass times number density times velocity, right? Okay. Let's look at the collision term. So the collision term are the last two terms. Okay. So minus me mi mu ie ui minus ue plus mi ne me ei ue minus ci. This will reduce down to e rho m me mu ei by n squared minus j. Okay. So you can just so you can just calculate this, where J is En with I minus Q. Okay, so this is how this term reduces to, and we just define this as 1 by sigma or eta, where sigma is conductivity, eta is the resistivity, right? So in that case, it will be E rho m J by sigma. Okay, so this is the J by sigma term in the in the what is it? Yes. So the J by sigma terms comes from the collision term, right? So if you also see there is E, right? So E is there, and then there is U cross P. So this term will somehow reduce to U cross P. And how? That's because U, the fluid velocity, is defined as MEUE plus MIUI. Simply the formula for the center of mass velocity. So when you have two fluids, well, you can consider electrons and ions as separate fluids, and you have two particles of masses me and mi moving at velocity ue and ui. So this is the average velocity, mass weighted velocity that you get, right? And therefore, MEUI plus MIUE is equals to ME plus MI times U minus MI minus ME times J by E. So this is the equation. Well, so this is max. So this is this term. So from here, you would get u cross b term and also a j cross b term, right? So there are u cross b term and then j cross b term. So we'll get both. So you see this term gives rise to u cross b and j cross b. These two terms give rise to the j by sigma term. This is E, and also let's see del t. So this term will give rise to 1 by E del J del T. So this is the del J del T term. There is E term. There is E is there. Then there is del cross del dot PE is already there. Okay. And so we are just neglecting the del dot PI, right? The ion pressure, which is negligible compared to the electron pressure. And right, what else? So we just need the this term del dot Ju plus Uj, which will basically come from this term del dot Ju plus Uj. Let's just show it once. Yeah. So if you just do this, you will get del dot Ju plus Uj. So you just have to expand this, right? So you just put the value of J from here. You just put the expression for J and you just put the expression for U, right? And just calculate Ju plus Uj and you will get this term. Okay, so yeah, I guess that is how we get to the generalized Ohm's. And well, in most of the cases, we can neglect the terms on the right hand side and we can just work with the left hand side. But in general, we this is the Ohm's law. Okay. And okay, so sigma. So there is a physical significance to the sigma. So since this term is coming from the collisions, and we saw that the way we define sigma is so 1 by sigma is um, mass of electrons and the collision frequency divided by any square. So our resistivity is equals to directly proportional to the collision frequency, right? Conductivity sigma is inversely proportional to the collision frequency. So the more collisions, more is the resistivity, right? So sigma tends to infinity means resistivity tends to zero. So resistivity zero means there is no resistance to the fluid, or in other words, it's an ideal fluid, right? So sigma tends to infinity is called as the ideal MHD approximation, right? So for ideal plasmas, sigma tends to zero. And if sigma tends to zero and we are just neglecting the right hand side, then the condition for ideal plasma reduces down to E plus U cross P equals to zero. So for ideal plasma, E plus U cross P is zero, right? Okay, so right, so that is the condition for ideal plasma. So this is the complete set of MHD equations which I have written. So del cross B, which is the Ampere's law. So the first four equations are the Maxwell's equation, Ampere's law, no monopole constant, del cross E is del B del T, Faraday's law, del dot E equals to zero, Gauss law. So in absence of free charge, right? So in presence of charge, this will be rho by epsilon naught. The mass content equation, which you derived, the momentum equation, which you also derived, right? So yeah, So here we are just neglecting the electric field. Right. So this is total derivative del dot del P. And this is the Ohm's law, and this is the equation of state. Yeah. So if you see, so these form a complete set of uh, equations which can be solved to obtain the values of these parameters. Yeah. Okay. So yeah, I guess now we want to move to a slightly uh, different topic. So, well, so about magnetic pressure. Okay. So, so you see the momentum equation, you have these two terms. Well, let's see over here. So if you have these two terms, right? So on the right hand side, you have this J cross P and del P. Now, we want to see what this J cross P term actually means. Right? What is the physical significance of this J cross P? Because this is the new term that we are seeing in MHD. In hydrodynamics, we only had the del B, we didn't have the J cross B term. So we want to see what that J cross B term is, and that's where magnetic pressure plays a role. So let's again go back to the whiteboard. Okay. So, right. So we'll start with the J cross beta. So let's write J cross B. So if you remember the Maxwell's equation, so del cross B is mu naught J. So J could be written as 1 by mu naught del cross B cross B. So so we just gonna use one identity which is this. So this is a vector identity. You don't have to memorize this, but I'm just writing this because we're just going to use this to simplify this expression, J plus B. Okay, so so using this identity, J cross B can be written from here as 1 by mu naught B dot del B minus del of B square by 2 mu naught. So remember the magnetic field is divergence less. So del dot B is 0. So we're using that property. And this is how J cross B comes out to be. Okay. So now what we do is we define one tensor TRS as minus PR PS by mu naught plus delta RS V square by 2. And writing it in just in tensor form. Okay. So this is the same thing. This identity set. Okay. Um, okay, let's see this. So, yeah, so this is the definition of TRS. Okay, now, so this is just how we define. Now we just want to see what del dot T looks like. So this will be del XR minus PR BS by mu naught plus delta RS B square by 2 mu naught. Okay, that's fine. So 1 by mu naught summation over R BR del PS del XR plus PS del BR del XR minus del XS of B square by 2 mu naught. Right? So now we are again going to use the property del dot B is 0, which means del BR del XR equals to 0, summation over R. So here R and S are again basically the coordinates. RS is X, Y, Z. Okay. So this is now using this property minus del dot TS will be yeah. So minus del dot TS will be 1 by mu naught summation over R R del TS del XR minus del XS B square by 2 mu naught. Right. Now, if you just see this, if we write it in vector form, this will be 1 by mu naught P dot del B minus del V square by 2 mu naught. Right? So now you see why we define T like that, because uh, this is what it turns out to be. J cross P is del dot T. Right? Now the momentum equation gets simplified a lot. We can write the momentum equation in conservative form like this. So this is the pressure tensor and this is the J cross P term. Together we can write it like this. Also we can write it in another form. So P dot del P minus del B squared by 2 mu naught plus P. So this is another form we can write. And this has a physical meaning actually. So this is the magnetic tension and this is the magnetic pressure, and hence can be clubbed with the gas pressure. And the gas pressure divided by magnetic pressure is another quantity which is defined as the plasma beta parameter, right? So this has been discussed in the lecture um, in some detail. So I'll not go into those, but this is how we can look at it in another way as well, right? So, right, okay. So now we're gonna do another thing, which is the induction equation. Right? So the induction equation actually uh, comes from the Faraday's law, I said, right? So you see, this is the induction equation talks about how the magnetic field evolves with time in the system, and it comes from the Faraday's law as well as the by taking care of the no monopole constraint, right? So we'll see how this induction equation comes about and what are the consequences of this. So let's go back to the notebook. So we'll derive this equation. Um, So, so del cross B is mu naught J, and mu naught J, like we saw, was E plus E plus B. So we're neglecting the RHS of the generalized Ohm's law. Now we take curl of the above equation. So mu naught sigma del cross E, yeah, del cross E plus del cross E cross B. And del cross B is del of del dot B minus del square B. I think we have done this identity before. Anyway, so right. So now del B del T. So from this equation, del B del T. Okay, so let's say that this goes to zero because of no monopole constraint. Right. Therefore, this side is just equivalent to del square E, actually minus del square E. So del V del T from Faraday's law is minus del cross E. And this del cross E from this equation, we just substitute del cross E in here. So this will turn out to be del cross U cross V plus 1 by mu naught sigma del square V. Okay, so this is 1 by sigma. Uh, if you remember, this is the resistivity. So this is also written as del V del T equals del cross U plus B plus eta del square B, right? And we can also define another parameter which is called the magnetic Reynolds number, which just says that what is the weightage of these two terms, like which one is greater. So if this one is greater, then the magnetic Reynolds number will be very high compared to this term. Whereas if the second term or the resistivity is very high, so the magnetic Reynolds number will be very low. Remember, in ideal fluid, the resistivity is zero. So therefore, for ideal fluid, or ideal MHD approximation, the magnetic resonance number should be very high. And this is, if you just do a order of magnitude calculation, we can see that this is mu naught sigma UL. So now there are two consequences. So as I was saying that Rm much greater than high, which is much greater than 1, which means that this is an ideal fluid. So in that case, so some there is one theorem which holds, which is called the frozen field theorem. So in absence of resistivity, what happens is that the flux remains constant. So okay. So if you have a bundle of fluid which travels from one place to another, so whatever the flux was there in the uh, initial surface, whatever flux that was passing through this surface, magnetic flux I'm talking about, which is phi d is integration of P dot dA. So P dot dA1, so if you consider this area to be dA1, this area to be dA2, and similarly, so P1, so integration of P2 at the second instant dot dA2, that will be constant. So uh, this is the frozen field theorem, which talks about, right? So in this case, the equation del B del T would just be del cross U cross P, right? Whereas if Rm is much less than 1, or in other words, the resistivity of the fluid is very high, then the equation will reduce down to this thing, right? So therefore, so this is a diffusion equation, right? So del B del T equals to some constant del square B. This is a diffusion equation. And the magnetic field diffuses, right? And what we mean by diffusion is that if you start with a magnetic field like this, and at some later time, the magnetic field will diffuse out and into a larger space, so just like this, right? So this is the solution of diffusion equation, right? And the time scale for diffusion is given by, if you just solve this equation, so this is the time scale of the diffusion. So mu naught sigma and L is the length of the system. Okay, so these are a few comments that I have to make. Okay, so now so this is the magnetic resonance number equation, and so this is the energy equation, right? So again, I will not derive this, but I will post it in the notes. So the way you can derive this equation is just multiply the momentum equation with velocity u. So therefore, you will see that you will get this equation. The physical significance of this equation is that the first term corresponds to the kinetic energy, second term is due to the pressure, third term due to the uh, magnetic field energy, and this is written in a conservative form, right? So the change in the total energy is due to the flux of the energy through the surface, right? And this is called the internal energy, right? The second term, actually, which is pressure divided by gamma minus 1. And the total thing is the enthalpy. So this is the definition of enthalpy. So another small thing that I wanted to point out is about magnetic helicity. So which is defined as A dot B over the whole volume. And this is considered to be constant uh, in case of an ideal fluid, right? So, so this was actually discussed in detail in the lectures, and I will derive how this is constant. This is something comes from the induction equation. If you just do a E dot of this equation, you can get to this equation. So yeah, I just wanted to mention this as well, but you can see the derivation lectures as well. Okay, now moving on to SSR variables. So okay, coming to the last part of our lecture is that uh, is this SSR variables. So why do we need this variable? So if you remember, so this is the momentum equation del P by rho. So here P is the total energy, total pressure, the pressure due to. Um, so if you remember this equation, right, and then we broke J cross P into 1 by mu naught B dot del B plus B square by 2 mu del dot B square by 2 mu, which we call as a magnetic pressure, which we can club with del P, right? So del P plus B square by 2 mu. And on the other hand, we have 1 by mu naught B dot del P. So that's what we have written over here, right? And there is we also included the um, viscosity term. And this is the incompressible condition, del dot B no monopole condition, right? And this is the induction equation. Right? So, okay. So, right. So, okay. Now, what we can do is that, so we'll later see why we are doing this analysis from the momentum equation and the induction equation, and why is this useful in some cases. This is basically just a transformation of variables and nothing very fancy. But why this transformation of variables has some physical significance that we will see. So now what we'll do is that we'll just write this equation like this. Okay. So this is just change of variables from capital B to small b like this. Right. And we can write these two equations like this. And then again, we change variables, and this is the main change of variables, and these variables are called the SR variables, right? Z plus and Z minus, which will be V plus P and V minus P. So earlier we had two coupled equation, right? Well, in V and P. So in the V equation, you could see that there is V terms, and V equation we have P terms. So this change of variables is important because this actually decouples them. We'll see what are some of the implications. Right? So if you just put this transformation into this equation, so we'll arrive at this equation. So right. And basically if you see this nu plus is nu plus eta, so which is nu and this eta, so this nu and eta by 2, and nu minus is nu minus eta by 2. So this is the mean dissipation, this is the difference dissipation, and again these two are the conditions del dot z plus del dot z minus equals 0 coming from these two conditions, right? So so the kinetic energy, if you see, will turn out to be z plus square plus z minus square plus 2z plus z minus. So this is basically z plus z minus whole square. The magnetic energy is z plus minus z minus whole square, and total energy is the summation of 2, which is z plus square plus z minus square. Okay. So right now the physical significance of why we're doing this is, so firstly z plus, if you see over here, it represents waves propagating along the magnetic field. So we have uh, decomposed these two equations into these two equations, which consists of waves moving along the magnetic field and waves moving against the magnetic field, right? Which is z minus. Now you also see that Z plus is affected by Z minus, whereas Z minus is affected by Z plus, and the nonlinear terms are separate separated over here. So you don't see this B dot del V and B dot del V over here. Right? So another thing is that cross helicity. Well, we already see that the total energy can be represented as very cleanly as Z plus square and Z minus square, right? So cross helicity conservation becomes transparent from here. So we'll come to that, what cross helicity means. And, uh, and the last thing is that energy transfer between modes is more apparent. So cross helicity is V dot B, right? So just like energy is Z plus square plus Z minus square, if you just do cross helicity V dot B, it will be Z plus square minus Z minus square. And you can represent the cross helicity in a form like this. So we just do this quickly. Here. We just see the conservation of cross helicity. That's so bad. Okay. So one more thing is that cross helicity is conserved only when there is no resistivity. So this is V dot B. So if you just to replace V with Z plus is Z plus Z minus by 2 and B with Z plus minus Z minus by 2. So this is how V dot D will be, and the equations will be this. We got del Z plus minus equals to minus del P. Now what we will do is that we will do Z plus times, we'll just multiply this equation with Z plus, the first equation. This will be minus Z plus dot del P. And we will multiply the second equation with Z minus Z plus dot del Z minus Z minus dot P. Okay. So, wait. So now, so we also know that the total energy is, so the modes of energy are Z plus minus whole square by 2. The total energy is the E plus E minus. Right? Okay. So, so you can just write these two equations with del E del T plus del dot E plus Z minus equals to minus del dot E Z plus 2 del dot Z plus. Similarly, for the other one, so let me write it down and then maybe explain. Q times Z minus. Okay. Okay. So what does it say is that so what does it say? So this is Z plus square. So this will be del E del T, right? And well, this term is a little bit complicated, but if you break this term, so this will be uh, yeah. So this will be uh, del dot Z bar. Well, if you break out this term, so this will be if you just, I mean, just use chain rule, right? So this is del P z bar dot del P plus P del dot z plus, right? And so yeah, so, and since this is minus, both will minus will cancel, and we'll have this term. So this checks out. Now the question is this term. How about the second term? How does the second term becomes this? So for that, I'll just show a quick derivation. So z plus I is z minus j del of z plus I del x j. So this is this term, right? Z plus dotted with z minus dot del of z plus, right? So this is this term. And if we do this, this will be z plus I, z plus I del x j. Okay. So I'm just taking this in, taking this in, and there will be 2, which is compensated by this half factor. And this will be half z minus j del of z plus square del x j. And this is actually, mm, well, the half is, so because this is e plus del x j. E plus is half z plus square. So this is z minus del e plus del x j. So that's what we have written. And we can take this z minus inside the del because del dot z plus and z minus is 0. Right? So this turns out to be the equation. And now if we write del e plus minus del e minus del t plus del dot e plus z minus minus e minus z plus e z plus minus z minus equals to 0. So this is e plus minus e minus, which is the helicity, and this is the flux of the helicity, right? So if you see this equation, sorry, this equation, so this is the del hc del t plus del dot fhc. So fhc is whatever is inside the bracket. So it says that the cross helicity is conserved in this case. And it also says that if z plus square is greater than z minus square, so it has positive cross helicity, which means more outward Alban waves. So as I said, z plus represents the outward Alban waves, z minus the uh, inward Alban waves. So here, so this should be less than, okay? So z plus square is less than z minus square, so then negative cross helicity, more inward Alban waves. If they're equal, so zero cross helicity, balanced turbulence. And the energy transfer rate is basically determined by z plus times z minus. Okay, so right, so we have seen this how the SSR variables are important in many cases. It brings out the physics, uh, and it has some interesting physical interpretation. So that is it for this week. And for the references, like these 3 books, as I said, for the plasmas, mainly this book is very good, Garnet and Bhattacharya. But in general, for astrophysical application, we can also look at these 2 books. Okay. So I guess that is it. I will post some of the notes of the derivations, for example, for the first and second moment, and the energy equation, right? And yeah, I guess that is it. Let me know if you have any questions. If not, you can end the call. Thank you for joining. See you next week.